What we've done so far is looked at systems of linear equations, and those were huge, right? We started off with 3 by 3 matrix, and then we went to about 100,000 by 100,000 matrices of coefficients and right-hand side vectors, and we solved those using the A/B thing. Last week, we explored the idea of what happens when we go from linear, which is nice, to nonlinear. And all of a sudden, things got really, really vastly more complicated. And you'll notice if you look at the equations we dealt with, there was one variable. One. Not 100,000, but just one. And even that took a bit of work to deal with. We came up with the bisection and the secant algorithms, as well as the roots function in MATLAB and F0 for some special cases. So that's the equation solving, the vanilla equation solving behind us now. What we're going to look at next is a totally separate topic, and it's going to be interpolation and basically fitting graphs to data. And we're going to do this a couple different ways. Interpolation is going to be the first way. We're going to spend 2 classes on this, and then we're going to look at the question a lot of you have already seen a little bit of before. We're going to put it in the MATLAB context, though, function fitting. But today is going to be about interpolation. All right. What is interpolation and why would we want it? Well, if you think from the design side, if you look at any CAD/CAM software, frequently you'll have contact surfaces that you need to get right. And then what happens in between those contact points or special locations on a surface, you don't really care so much. You honestly don't. You just want it to look nice or be smooth or have some other properties that make it reasonable. And one of the examples of that would be a roller coaster track. We might specify where the support points are, and as long as we get a track that fits smoothly between those supports, we're happy. We don't really care whether it's 5 millimeters one way or the other. We just want the basic shape to look reasonable. So that idea of joining points together in a smooth way is called interpolation. And I just want to remind you that's going to give us a curve exactly through the data points. And so it's not function fitting, which goes near the points. Some examples that you'll see out there when it comes to numerical simulation. All of these come from numerical simulations, except for these 2 guys down here, which are from data. The idea is you might have some method, like, say, finding the heat distribution in a plate, and it might work in a fairly coarse grid. And you go, OK, well, that's great, but I want to figure out what's happening in between those grid points. The interpolation will smoothly fit inside that. We're going to look at single variable interpolation. These are examples of 2 variables, but the same idea applies. It's an easy generalization. So if you have some rough estimates and then you want to get a smooth fitting in between, that's, again, another way to talk about or use interpolation. Quick bit of terminology. The points that we know are called any of the above. Control points, knots, nodes. These are all terms that are used in the literature for depending on where the historical roots were. But the idea for us is that they're going to be a sequence of XY pairs. So a sequence of XY coordinates, that's going to be our starting point. Now here's the underlying problem with interpolation. If I give you 4 sets right here, 4 sets of control points that are identical, they're absolutely identical. How many interpolations can I make? How many do you think? Lots or very few altogether? Lots. OK. Someone give me an idea of how let's take the top left corner, and we'll build an interpolation. How would you like to connect the dots in that first graph? Yeah. Bunch of straight lines. Absolutely. Doomph, doomph, doomph. That satisfies our criteria of being an interpolant because it goes through the points and it's a function in between. That's lovely. What's sort of a downside to that particular choice? What might you not like about it? That might be fine for you, but you might not like it on some grounds. If this is a roller coaster. Yeah. It would kill all the riders. That's a downside. We don't like that, especially this point down here. So what characteristic of the graph makes it deadly? Yeah? Sudden changes in slope, exactly. And one of the ways to characterize that is the smoothness. When I have a brusque thing like this, I have a cusp, and that's something where the derivative changes dramatically in a short period of time. So we might want to say is, well, let's smooth that out. Let's have, something like that. That would be a perfectly reasonable interpolant. Still goes through the points, but isn't a straight line approximation. Both are perfectly good for some things, but we might want to trade off between the two. It's also worth noting, of course, that we could have a graph that does this. That is an interpolant. Is it one we want? Probably not. In some sense, we also recognize that we want smooth. This is smooth. It doesn't do that much. There's no sharp corners in it. But it also doesn't seem to follow the data. So there's something sort of inherently unsatisfying about that. So we have some ideas of what we like and don't like. But the problem is going to be there's not going to be a single best answer for every case. Sometimes that straight line thing is actually what you want. And in fact, if you zoom in on MATLAB graphs, all the graphs that we plot are actually drawn as little segments connected together. But if we take enough points, then those straight line approximations look smooth if you kind of step back far enough. So it's amazing how many times we're actually really, really happy with straight line approximations. However, there are definitely other times where we want something more like this. So smooth, goes to the points, but we're going to have to see what the pros and cons are of various ways to build it. There might be some other choices. This one might go a little bit further down than back up. So we might get a variation on the theme that still is smooth, still goes through the points, but is a little different. Is one better than the other? Well, depends on what you're doing with it. So we'll have some awkward balances or factors to balance off when we do these. Okay. That's the idea. Now let's talk about implementation. From that, we're going to have some things that we're aiming for. We would like to have a continuous function. If we're drawing this, it should be all one pen stroke. The continuous derivative is going to mean no cusps. The smoothness is actually a little layer. It's harder to see, but it turns out if you look at the second derivatives, so the curvature, that will be continuous. That'll make a graph actually look smoother even than no cusps. And we're going to be looking for a function. So we're going to look for, as x moves across, I want some graph that I can draw like y equals f of x. All right. With that in mind, what kinds of functions? So we're going to build this out of tools that we already know. Well, let's list off some families of functions. What kind of families of functions do you know? Yes. Pardon me? Linear, absolutely. Linear functions. Sinusoidal, sine, cosine, exactly. What else we got? Polynomials. We're running out. Sorry, here. Logarithmic, thank you. I thought for some reason I said quadratic there. Logarithmic. And its partner? Exponentials, exactly. Those are the big ones. I mean, you could get into inverse trig, but no one really wants to do that. Okay, so I think those are the highlights. Any other big families that we're missing? That you can think of? Any function you imagine that doesn't fit in that category? Those categories? Pardon me? Piecewise? Fair enough. I would say that's a variation on all of these, that we could make any of these or connect any of these with piecewise. But you're right, we'll need piecewise actually before we're done here. Power functions. I would fit those under polynomials. Oh, I guess you could have other powers. You're right. So you could have x to the 3 halves and that kind of stuff. Non-integer powers. Excellent point. Other power functions. Okay. But we're scraping, right? This is a pretty reasonable set. Which one do you think would make a good general purpose interpolating function? If you had to pick one out of all of these, yell out your favorite. Just now. Polynomials, yes. We love polynomials, right? They do the S-bend. They can have 3 bends if you do a cubic. You can have 4 bends if you have a 4th order. They're really, really flexible. Logarithmic, exponential, they basically do the same thing. They grow. That's all they do. I should emphasize that sine, cosine, while whoops, that wasn't right. How do I undo? Undo. All right, fine. Sine, cosine. Those have a very special place in interpolation. Does anybody know when sine, cosine families of sine and cosine functions show up in math a lot? Yeah?
Is that like Fourier?
Yes, Fourier. Fourier transforms. Who here has heard of Fourier transforms? Everybody, good. Okay, so more you should have known that. This is like polynomials, but for time series. All right. So sine and cosine are a great foundation, but they're more for time series where things repeat themselves, or we think they kind of repeat themselves over time. Polynomials are the generic one for just graphs, things that just do what they do.